What are the best methods for PID controller design in electrical engineering? If you are curious about how to design an effective proportional integral derivative controller in electrical engineering, you are in the right spot. Let's break down the best methods to achieve optimal performance in control systems. First, understanding the basic concepts of a PID controller is essential. The proportional term, often referred to as P, adjusts the output based on the current error. This helps speed up the response time. The integral term, known as I, addresses past errors by accumulating them over time, which helps eliminate any steady-state offset. Finally, the derivative term, or D, anticipates future errors by looking at the rate of change, which minimizes overshoot and oscillations. Together, these three components work to maintain precise control over electrical parameters like voltage, current, and temperature. Now, let's look at some common methods for designing a PID controller. One popular approach is the Ziegler-Nichols Method. This heuristic tuning method starts by setting the integral and derivative gains to 0. You then increase the proportional gain until you observe sustained oscillations in the system. From there, you can measure the ultimate gain and oscillation period, which will help you calculate the appropriate gains for your controller. This method is a great starting point for tuning PID parameters in various electrical systems. Another method is the Cohen-Coon Method. This technique uses a process model to estimate the necessary parameters and derives the PID gains based on the specific dynamics of the system. It is particularly useful when you have a good model of the system behavior. For those who prefer a hands-on approach, the trial and error method allows you to manually adjust the gains based on the observed system response. This is often used when accurate models are not available. As you design your PID controller, consider some advanced techniques. Gain scheduling involves adjusting the PID gains dynamically based on different operating conditions. This ensures that the controller maintains optimal performance across various states. Feedforward control is another technique that can improve response time. By anticipating disturbances, it works alongside feedback to enhance overall system performance. Cascaded PID control is useful for complex systems with multiple interacting variables. This method involves using several PID loops in series, which is common in applications like motor drives. When implementing your PID controller, remember that it is often done using microcontrollers or digital signal processors for real-time control. Sensor feedback, such as voltage or current measurements, provides the necessary input for the controller. The output then adjusts actuators, like pulse width modulation signals, to control electrical devices effectively. Tuning your PID controller requires careful consideration of system nonlinearities, delays, and noise, which are typical in electrical systems. By understanding these factors and applying the right methods, you can design a PID controller that performs reliably and efficiently in various applications.